First question we have from Schrodinger equation. This is the application of Schrodinger equation for a particle in a one-dimensional box. So here the question says set up the Schrodinger equation for a particle in a one-dimensional box. So what we need to find out? We need to find out the wave function of the particle in a one-dimensional box using the Schrodinger equation. For this purpose, what we have done, we have taken, let's say, this is our 1D box. The length of the box is, let's say, is x equal to 0 to x equal to a, and the particle is inside the box, which is free from any kind of interaction. Therefore, what we can consider that the potential energy inside the box is 0. And as the particle cannot exist outside the box, what we can consider that the box, it has infinite amount of potential energy along its walls. Therefore, V, the potential energy along the wall, is equal to infinity for both the walls, so that the particle cannot escape from the box. Now, if we consider these assumptions, so first what we have considered the particle is inside the box, and we have considered inside the box the potential energy of the particle is 0. And another thing what we need to know is beyond the wall of the box, the wave function of the particle is 0. So this is called the boundary condition. The boundary condition is psi equal to 0. The wave function of the particle is 0 beyond the walls of the box. Because the particle is inside the box, it cannot be outside the box. Therefore, the wave function must be 0 outside the box. Now, what we are doing, we are using the Schrodinger equation. So, this is our Schrodinger equation for one dimension. We have del 2 psi del x square plus 8 pi square m upon h square E psi equal to 0. We remember there is a V, but as V equal to 0, this becomes only E psi. Right? Now, let's consider this to be k square. So, let's say k square equal to 8 pi square m upon h square into E, and we rewrite this equation in this form. So for this kind of a differential equation, the solution is psi is equal to a sin kx plus b cos kx, where a and b, these are constants. Now what we need to do here, we need to find out the value of these constants a and b. For this purpose, we use the boundary conditions. What was the boundary condition? We try to remember. The boundary condition was outside the box, the wave function of the particle is 0. So if we consider x equal to 0, and then the psi is equal to 0, and if we consider x equal to a, again psi equal to 0. This was the boundary condition. So if we are using the boundary conditions, what happens? Look, so first at x equal to 0, psi equal to 0. This is our first boundary condition. And we put the values 0. So instead of x, we write 0. So sin 0 becomes 0. So only b cos 0 becomes equal to 0. Here we remember cos 0 cannot be equal to 0. Therefore the constant b has to be 0. Therefore our psi becomes a sin kx. Let's say this is our equation number 1. Right? Now we need to find the value of a. So again the another boundary condition we have a sin kx equal to 0 at x equal to a. Because we remember at x equal to a, psi is equal to 0. Right? So a sin kx equal to a sin ka equal to 0. Here we have two terms. One is a, one is sin kx. So either a equal to 0 or sin ka equal to 0. Now let's say if a equal to 0, what happens? If a equal to 0, then the whole psi value becomes 0. Meaning the wave function of the particle inside the box becomes 0. But we already know the particle is inside the box. As the particle is already inside the box, the wave function cannot be 0. So this constant a cannot be 0. Therefore, sin ka must be 0. If sin ka is 0, therefore what we can write? Sin ka equal to 0 meaning sin n pi, where n is any whole number like 1, 2, 3, 4 and so on. Therefore, k becomes equal to n pi and k becomes equal to n pi by a. Right? Therefore, from equation number 1, psi becomes equal to a sin n pi x upon a. This is our equation number 2, let's say. And finally, from this portion, we need to find out the value of A. how do you find out the value of A? So to find out the value of A, we'll be using a technique called normalization. In normalization, what we do? In normalization technique, we consider the probability of finding the particle inside the box is 1. The probability Px of finding the particle inside the box, meaning from 0 to A, the probability of finding the particle inside the box is equal to 1. Therefore, the probability is given by chi square, wave function square, that gives us the probability of finding the particle inside the box. Therefore, chi square dx is equal to 1, and chi is, we already know, chi is equal to a sin n pi x by a. Therefore, chi square is equal to a square sin n pi x upon a square dx equal to 1. Now, this sin square, we know this is nothing but equal to half 1 minus cos 2n pi by 2n pi x upon a. And finally, what we have? We have a square half integration 0 to a dx minus half integration 0 to a cos 2n pi x upon a dx. Right? And finally, if we integrate, this becomes a square half x from 0 to a minus half sin 2n pi x by a upon 2n pi by a, which is a constant, from 0 to a is equal to 1. Here, instead of x, we put the value a, so it becomes a by 2. Here, look, if we put the value a, then it becomes sin 2n pi, which is 0. If we put the value of x 0, sin 0 is also 0. So the second term as a whole is equal to 0. For a it is 0, for 0 it is also 0. Therefore we can write a square into a upon 2 minus 0 equal to 1, or a square into a by 2 equal to 1, or a square equal to 2 by a, or a equal to square root 2 by a. And finally we put the value of a in equation number 2, that becomes chi equal to square root 2 by a sin n pi x by a. So this is the normalized wave function for a particle in a one-dimensional box using the Schrodinger equation.